Hi everyone, welcome to Modern Optimization Methods. Today we will introduce the second part of Chapter 8. We will discuss an example to show how we can derive the KKT condition by the abstract form. Firstly, let's recall that we are considering the constraint optimization problem, which we try to minimize fx, and we have some equality constraints and inequality constraints. So compared to the abstract form, this example is actually sort of a more practical example, okay? So the abstract form that we introduced in the previous part is that we try to minimize the function f about x, where this x is in some space, okay? And meanwhile, we got abstract constraints, gx in some cone, right? So this is the abstract form. And now, the aim is that we try to reformulate or derive the KKT condition using the abstract form to see what is the KKT condition of this problem like, okay? Now, we need to transform this form into the abstract form, okay? In other words, we need to specify the capital X as well as the variable x, small x, then the constraints gx, as well as the cone k here, okay? Now, let's take a look at how we reformulate this problem into this form. So, for the constant gx, we actually have some equality constraints c1 to cm, as well as some inequality constraints h1 to hk. And for the cone k, actually, for equality constraints, the cone is actually the 0 point, right? Which is actually a cone as well. And for the inequality constraints, the feasible region or the cone is actually that it lies in the non-negative orthant, Rk plus, right? So this becomes the Gx in K, okay? Now, to derive or to apply the KKT condition, we need to first know that the dual cone of K, okay? So for the dual cone of K, recall that K is the product of the two parts, right? So the dual cone is actually the product of two parts. One part is the dual cone of 0, which is the full space Rm. Another part is the non-negative orthant, whose dual cone is actually itself. So for non-negative orthant part, it is self-dual actually. So after knowing the K star, the dual cone, then we can specify the feasible region for the parameter mu, which is a Lagrange multiplier, okay? So for Lagrange multiplier, it must be the same size as gx, okay? You got lambda, this block will be containing m components, and for the block V, it will contain k components. For this lambda, it should lie in Rm, and for V, it should lie in the dual cone of Rk plus, okay? So recall that the abstract form for KKT condition is simplified as the following. So this is the result we obtained in the last part, okay? So we got a gradient to be 0, and the feasibility of x bar, then mu bar in the dual cone, finally the inner product of the two parts is 0. Then we will derive one by one the conditions, okay? So for mu in the dual cone, it actually means that the lambda block is in Rm, which is free, okay? And the V block is in non-negative part, all right? And for Gx in K, it is equivalent to the equality constraints and inequality constraints, okay, which is obvious. And now for the inner product of mu and G to be 0, okay, so if we take the inner product and expand it, then we can see that it is actually equivalent to two parts. The first part is equality constraint part, and the second part is inequality constraint part. Notice that the two parts equals, the sum of the two parts is 0. It's actually equivalent to the fact that only the inequality part is 0. Because x is a feasible point, implying that Cix is 0, okay, which means that this part is cancelled out, and the left one is for the inequality part. Also, for the sum of the inequality part, you can see that for each sum item here, the Vi is non-negative and Hi is non-negative as well. So the sum of non-negative to be 0 is equivalent to each Vi Hi to be 0. Okay? Therefore, we can see that the inner product of the two terms to be 0 actually is equivalent to the following three results. So the first one is Vi is 0, meaning the complementarity condition. Meanwhile, we require Hi to be non-negative and Vi to be non-negative. Moreover, for equality constraints here, we require that Ci to be 0. Okay? So this is what the inner product means. Now, to summarize, we already derived that Cix to be 0 and Hi to be non-negative, Vi to be non-negative, and also the complementarity conditions. And for the first part, so the Lagrange multiplier here, if we take the gradient with respect to x for Lagrange function, then we can get the same condition as the KKT condition in chapter 7. And now, this is actually the KKT condition we discussed in chapter 7. In other words, by using the KKT condition for the abstract form, we can recover the KKT condition in chapter 7. Okay? Now, let's consider an example, which is again the linear programming. Okay? So for linear programming, in this example, we consider equivalent constraints as well as non-negative constraints. Okay? So we will look at what is the KKT condition for this part. Now, the Lagrange function is the same as before, so we have the objective function minus the inner product of the two parts. Okay? The first part is for equality constraints, which got Lagrange multiplier lambda. And the second part is minus mu multiplied by x, where this mu corresponds to the non-negative constraints. And now the KKT condition, we can use the abstract form, or we can use the form of chapter 7. For each form, we can all reach the following condition. The Lagrange function, taking gradient with respect to x, will reduce the following equalities. Then the feasibility condition Ax equals b, and the non-negative constraints x greater than or equal to 0. Finally, is the constraints that this mu must lie in the dual cone of non-negative orthant. Then is the optimality condition for the two parts mu and x, which is actually the complementarity condition. Okay, so this is the KKT condition for linear constraints and non-negative constraints of linear programming. Now, let's make a brief summary about this part. In this part, we actually show two examples, and by the two examples, we show that how we can use the abstract form to derive KKT conditions, and how we can get connections with the abstract form and the form in Chapter 7 for KKT conditions. Both of the two forms, they are very useful in optimization problem. Okay, we stop here and see you next time.